Good afternoon to all of you who are here present with us at the University of Pretoria, and then also to everybody who has logged in online. You are all very welcome, and it's great to have you with us. My name is Hannes Grawe. I'm the acting head of Department Civil Engineering, and it's my honor to introduce today with us Professor George Markou. He's associate professor here in our department, and his speciality is in structural engineering, and specifically also one of his research interests, earthquakes. So I think he is ideally qualified and experienced to present this lecture today. So Professor Markou, thank you very much. I know you've put in a lot of effort to prepare this presentation. We are looking forward. Thank you very much.
Thank you. All right. Before we begin, if anyone has a question, you can type it if you don't have a mic, or at the end of the session, you can raise your hand and I will give you the floor. Just let me know if you can see my screen. Okay, great. Thank you very much. For those that don't know me, my name is George Markou. I joined our university in September 2018, and my field of expertise is in computational mechanics. We are doing a lot of work in numerical modeling and, of course, earthquake-resistant design of structures. I would like to thank everybody that is here and our head of department, and also I would like to thank Prof. Christo Venter for having this interesting conversation a few days ago, and he suggested that we offer this lecture, and therefore this is how this came to fruition. So the devastating earthquakes in Turkey, this is what we are going to cover, and given the fact that we have also students online that were not introduced to this part, I will say a few things about earthquakes and how do they occur. Then we're going to say a few things about the main earthquake events that happened on the 6th of February 2023. Then we will analyze the main event, the accelerogram, and then show a few things on how reinforced concrete structures should behave, even though they are not designed to withstand significant earthquake loads. And then we're going to enter the world of damage and destruction that occurred in Turkey. And we will close by saying a few things about the case of Zrin City, and then some conclusions. And at the end, you will be able to ask any questions, and we will have a discussion accordingly. So what are earthquakes and how do they occur? As you can see, this is the these are the major layers of the Earth. We have the lithosphere, which is composed from the crust and the upper solid mantle, and below that, the mantle is, in this case, very, very soft, and it has a relative motion, and this is what causes the plates, in this case, to deform, and therefore the deformation that causes in this case, the intercontinental drift, as you can see here, the animation 200 million years ago, and this is how Pangaea, which was a single continent, formed into the modern map. The interaction between these continents and the tectonic plates cause earthquakes, and of course, the movement that causes the tectonic plates to interact increases the stresses at the boundaries, and when these stresses reach to a specific limit, then we have the rupture. Therefore, the rupture, right, the focus, in this case, causes an entire surface to move, and therefore PNS waves are generated, and this is how the waves, earthquake waves are, in this case, generated, and they reach us and we feel the vibration and the movement of the ground. The waves reach us first, those waves come later, and mainly these waves are the ones that are measured by accelerometers. Now, on the 6th of February 2023, in the morning, 17 minutes past 1, a 7.8 moment magnitude earthquake occurred in this region between Kahramanmaraş and Gaziantep. And 9 hours later, another earthquake of 7.5 moment magnitude occurred in this region northern of Kahramanmaraş. These events caused, in this case, more than 3,500 aftershocks. This figure shows the epicenters of earthquakes that had larger than 4.5 moment magnitude. And as you will see here in a video that I created for the needs of this presentation, it starts and it shows by using EMSC website data, it shows the epicenters from the 5th of February until the 28th of February. As you will see with red dots, this is the 6th of February, 7th of February, and so on. More than 3,500 earthquakes occurred due to this phenomenon. And of course, as you can see, Cyprus is nearby. On the west side is Greece, which are countries that are extremely concerned with what have happened. And of course, the seismic activity in these regions also activates other faults in the southern and western area. Like in 1999, we had this mid-earthquake, which also caused earthquakes in Cyprus and Greece. Now, Prof. Athanasios Ganas, which works as a researcher, and he's the director there in the Athens Observatory, he sent me a couple of days ago this rupture pattern of the fault. And as you can see, the shape follows the video that we've seen in the previous slide. The depth here is 20 kilometers. And this is how the pattern was developed from these scientists, which is a work that was submitted for publication to Seismic on the 20th of February, if I'm not mistaken. So in this case, we have, as we said before, the intercontinental plates. This is where the earthquake occurred. It was a shallow depth strike slip faulting that produced a 7.8 moment magnitude, and the second one, which was 7.5, several 6 and 5 moment magnitude earthquakes. An estimation of 250 kilometers by 20 kilometers depth was the surface, the rectangular surface of the ruptured fault, around 5,000 square kilometers. And of course, it is attributed to the triple junction of the Anatolian, African, and Arabian tectonic plates. This is the eastern Anatolian fault, as we can see here, and this is where the two main events occur. Now, the accelerograms and in this case, the components of the accelerograms that I used, I got them from the engineering strong motion database from the station KHMN, which was located 25.5 kilometers from the epicenter. And of course, the epicenter, as you can see, shown here again, where the east-west accelerogram derives a maximum acceleration, peak ground acceleration of 0.52 g, and the north-south component is 0.62 g. Of course, for those that are experienced with earthquake-resistant design, they know that our maximum peak ground acceleration here in South Africa and Pretoria is 0.2. And in Cyprus, which is an actively seismically active country, 0.25. So these are really large magnitudes, and the Z component also was very large, reaching almost 0.5 G. Now, by using any software out there, I use Seismospect. I developed the elastic spectrum diagram, and as we can see, especially for the north-south component, we even reached 2G. But of course, this is an elastic response. And for those students that, again, did not reach the point where they will learn what is the response spectrum diagram, we have our structure, right? We can calculate the fundamental period. And through this diagram, we can travel and run through the time which is the x-axis, and say if I have a 4-story building reinforced concrete structure, 4 stories divided by 10, about 0.4. So if I come here, I know and I can calculate the expected acceleration. Mass of the structure multiplied by the spectrum acceleration will give us the inertial forces, and this is how we can calculate the maximum expected loads instead of performing a non-linear or a linear dynamic analysis for each and every accelerogram. So this is just a small parenthesis here. Now, if you want to see where the Eurocode 8 is located, I use the 0.25 G as a peak ground acceleration. Important class 1, of course, these are buildings with of minor importance. And of course, the ground type was C. This led to a maximum of 0.6 G in the elastic spectrum again. And if, let's say, we go to importance class 4, which are, in this case, hospitals, fire stations, power plants, we can reach up to 1 G. Again, in the elastic spectrum diagram. But our lives are non-linear and not elastic. So in this case, if we assume from Eurocode 8, and a similar value for the behavior factor here, in the case of SANS 10-160-4, then we can see here that this is the inelastic spectrum diagram for north-south and east-west. And of course, with the dashed line, this is the median spectrum. So if we take into consideration what I said before, approximately number of stories divided by 10 will give us the fundamental period of our reinforced concrete structures. Then this says here that if you are 25.5 kilometers away from the epicenter of this earthquake, and you have a 1 or 3 up to 3-story reinforced concrete building, you're done. Your structure will be destroyed. And if you have a 4-story up to 15-story structure, then you will expect the development of extremely large inertial forces. So the question here is, what did we have in the case of Turkey? Did we experience failure of short buildings or tall buildings, or both? Then one will say, all right, I designed my structure with 0.25 G. What is the actual strength? Because we have all those safety factors integrated there. So back in the time, after I finished developing the first phase of Recon and FAIR, I said, all right, let us check what the Eurocode will provide to us. So I designed a random structure, 2-story reinforced concrete structure, which I used in order to design, as you can see here, this is a 3D frame as it was developed in the finite element analysis software. And then I used the geometry and Eurocode 8 in order to calculate the reinforcement. I use a commercial software. So these are the reinforcement for the columns, and the beams, they had stirrups 8 millimeter every 10 cm, and the longitudinal reinforcement were practically 2 to 3 bars, 14 milli in diameter, top and bottom. Some of them, they had 16 milli. So I created a 3D detail model, as you can see here in Recon and FAIR, with hexahedral elements to discretize the domain of concrete, and the bedded rebar elements in order to discretize and model each and every rebar according to the design that derived from Eurocode 8. I performed a pushover analysis, and what I discovered was that the actual load that I needed to apply in order to make this structure fail was 3 times larger than the actual design. So practically, between 2.5, 3 times is the over design that we get the final product if we assume that this is the earthquake that we expect to get. So this shed a lot of light on why structures don't fail. They do develop damages, but they don't fail if we have very large earthquakes. Now, these are the solid bone mesostrains as they occurred from the analysis. And of course, Recon has the ability to capture cracking, and this is Recon and I, through which we can show the crack pattern as it was developed. And this, by the way, is extremely old work back in 2010. And as you can see, our structure develops damages, cracks, significant cracks in this case in the area of the main shear wall where the elevator is. And after output 8 and output 9, we have actually very, very large deformations, but the structure doesn't fail. Why? Because it behaves in a ductile manner. And of course, one might say, okay, but this is a two-story building. What about bigger structures? As you can see here, this is the hysteretic loop of a four-story building that was actually tested in a laboratory, and we modeled it under cyclic loading. This is a 100-meter span reinforced concrete bridge that was initially stressed monotonically, and then we analyzed it also under cyclic loading condition with the same approach in order to calculate the fundamental period of multi-story building, including soil structure interaction, wind turbine structures by performing pushover analysis, including soil structure interaction. This pile cap is 2 meters thick. This is a nuclear reactor building that was also tested under the Chile earthquake, which was an 8.8 moment magnitude. And we performed the analysis here in order to see if these nuclear reactor buildings are safe for the case of mega earthquakes. And of course, now we are working with this guy here a lot. AI is his name, and fortunately or unfortunately, there is a high chance all these will become history, and the predictive models that we will develop will not require any finite element analysis. And of course, one of the main goals, as you can see, this is a model that I've developed of the Burj Khalifa, is to be able to perform full nonlinear dynamic analysis of structures like that in order to evaluate them. This model has more than 14 million hexahedral elements and more than 22 million nodes. And of course, this does not include piles and soil domain. Now that we established how far the technology has reached in terms of earthquake resistant design, and we didn't even talk about modeling and experimenting with seismic isolation, one will wonder, okay, do we know how structures are expected to behave, even those structures that they are not behaving in a ductile manner, they were not designed based on modern technology? So I decided here to show you this experiment that was performed in the largest seismic table in the world, which is in Japan, E-Defense. And this research group, led by Prof. Kim, designed a normal reinforced concrete structure, which is 6 stories. And in this case, designed it with the old Japanese code. This experiment was in 2006. And also they incorporated flaws like a short column, and the design did not foresee for high ductility nor well-confined structural members. So they used less than 1% longitudinal reinforcement in girders, the same thing for the columns. The stirrups were merely 0.3%, and the shear walls that were included in this structure also for vertical and horizontal reinforcement, 0.32%. And of course, the material here, 30 megapascal here in our laboratory, is something that we cannot achieve, our students. Why? Because they always get higher strengths, at least 50. So 30 megapascal is, for a 6-story building, is not high strength, let's say, right? So what they did, they applied 6 different earthquakes in order to investigate the mechanical response of this structure. And the 5th was 100% of the Kobe earthquake, and the last one was 60%. So this earthquake, by the way, in 1995, killed 6,434 people and more than $200 billion in damages. And as we can see here, this is the experiment. This is an overview of this is 100% of the earthquake. And now we are going to see also the damages that occurred. This is, of course, a standard short column failure due to the development of significant strains, shear stresses and strains. And of course, we should develop and perform design that will avoid that type of failure. But in that case, they did it intentionally just to see how the structure will perform. Also, a corner column that develops also damages. And we all know that this should be avoided. You should decouple the reinforced concrete wall from the column. And again, this is how, and not even a medium ductility shear wall behaves under these seismic loads. Thereafter, they applied 60% of this earthquake. Now the column is already lost, right, if you recall, and the framing system that is now damaged has to resist 6% of this relatively large earthquake. And as you can see, the column is completely lost, but again, the remaining of the concrete, the drop beams, the shear walls are there to provide strength, and this structure did not fail completely nor collapse. As we can see here, extreme spalling occurs, but again, even if we don't have significant high confinement, the column maintains its integrity and it's able to resist the superstructural loads. Some sliding, as you can see here at the base, diagonal cracks are visible, but our shear wall is fine. So this is how reinforced concrete structures usually should behave, even though they are not designed to withstand significantly high earthquakes and behave in a highly ductile manner. Ductility, the ability of a structure to deform beyond the first point of damage. In 2000, Japanese, their government and their municipality approved the revised design code. On the 11th of March, the Tohoku earthquake occurred, and this earthquake was a 9.1 moment magnitude that occurred 70 kilometers, approximately 75 kilometers out far from Sendai. The aftershocks of this earthquake were larger than the main events of the Turkey earthquakes. 7.4, 7.9, and 7.7 in just 20 minutes. These are the aftershocks, and they are larger than the earthquake, the earthquakes in Turkey. And just for you to understand, the difference between an 8 and a 9 in the moment magnitude releases 32 times more energy compared to an 8 moment magnitude. We're talking about a huge difference. So what happened there? Buildings mainly collapsed and were destroyed due to the tsunami that followed, and not due to this massive earthquake of the 9.1 plus the very large aftershocks, which of course shows that our codes work and we know how to design, in this case, against earthquakes. And unfortunately, the tsunami killed a lot of people, almost 2,000, 2,500 are still missing. So now that we know how structures should behave, even structures that they are not designed to be extremely and highly earthquake resistant, let's go see what happened in Turkey. Now, officially, 48,110 dead people were reported, most of them in Turkey, of course, and I found this information on the a report on the 22nd of February. Some estimate 50,000 dead, some others 100,000. A few, I think a week or 10 days ago, I saw an interview in Greek TV of an analyst that was talking about 200,000 dead people. This is like 5 times more than the deadliest war of Turkey's recent history. It is certain, definitely, that we will never know how many died, and a lot of people will never be found. More than 100,000 were injured. And of course, another big problem was that this occurred during winter time. And as you can see, hypothermia and sub-freezing temperature made it very difficult for people to get rescued. On top of that, it's estimated around 13.5 million have been affected, and 4 million buildings have been either damaged or collapsed. Most of them damaged, of course, and the number of those that they were trapped under the rubble cannot be estimated. And at the beginning, the first days of the incident, citizens were actually tweeting whilst being under the rubble, asking for help. That was complete tragedy. Now, the Ministry of Environment, Urbanization and Climate Change inspected 763,000 buildings, out of which 41,791 were completely destroyed. And this displays, of course, roughly 150,000 people in the 10 provinces that they were affected. I will show you in the next slide the 10 provinces that were mainly affected. Other than the damaged buildings and structures that will have to be demolished because they cannot be rehabilitated or, and in this case, in other words, fixed, we have the estimation of the direct physical damage, which was based on the worldbank.com 34.2 billion US dollars. This is 4% of the GPT, the country's GDP. And of course, the other big problem was that their cemeteries were full and they weren't able to find space to bury their dead. So this was an article from The Guardian on the 10th of February, 2023. As you can see here, we have Adana, Hatay, Kahramanmaras, Gaziantep. Apologies, Özlem, for my pronunciation of the provinces. This is Malatya, and of course the epicenter of the 7.8 earthquake can be seen here. So these are the 10 provinces that they were mainly affected from the two main events. Now let's go see how the structures failed from feeds from mobile phones and cameras of people that they were there and filming their own structures collapsing. Of course, viewers' discretion is advised because this is not a movie, this is real life. So this is a damaged 5-story on the 6th of the Feb. And this is the failure. We will see the failure again from another angle. As you can notice, this is a vertical failure. This is like a demolition, which should say a lot. Again, another video of people running left and right. This is a multi-story building that again failed completely in a vertical manner. No residual strength whatsoever, completely destroyed. And as you can see here, some of the buildings partially collapsed. People were in the middle of the street, and wherever they were looking at, they were experiencing vertical collapses, buildings that they were collapsing in a vertical manner. This is again another case of a completely vertical failure. Makes no sense whatsoever. This is not how reinforced concrete buildings behave. And of course, after all this experience, people didn't know if other buildings will collapse after the earthquakes have passed by, of course. And as you can see here, these are buildings after the earthquake, and look at this. Half of the building, the multi-story building, collapsed. So the camera will zoom in, and I will pause it for a bit. This is supposed to be a reinforced concrete building. This is supposed to be here. This is supposed to be a reinforced concrete slab. Do you see any rebars? Here, here. This is supposed to be a reinforced concrete column. Do you see any rebars? No rebars. Where is the reinforcement? So let's continue. This is Antakya, an entire neighborhood. As we can see here, we have 4 5-story buildings, right? Which are entirely destroyed, and some of them are still standing. This is southern eastern Turkey. This is in Antakya. It's very important for the case of the Ezrin city, just to remember, remember Antakya, remember Hatay, and Adana, these 3 names, in order for us to be able to explain what happened in the Ezrin city and why it's important. Now, this is the case of the Yaman province. As we can see here, people are sitting in front of their collapsed building, trying to warm themselves, bit of snow as well. This is Mr. Mehmet. 5 members of his family are trapped in this building, sitting there hopeless. unfortunately, words cannot describe what we see there. Several reports as well stated that owners in shops remove columns to create space for their shop. This is a case in Antakya, a multi-story reinforced concrete building which lost its ground floor and first floor. And the same thing we can see here where this soft story mechanism occurs is either due to illegal interventions or due to bad design. We have a soft story, earthquake strikes, we lose that entire story. First floor becomes the ground floor, the second becomes the first, and so on and so on. So this is something that we know. Now, some claim, and I saw some colleagues, especially in Greece, that they were interviewed by many journalists, said there was no way to save these structures. No code could have helped them. They told them, but we saw buildings failing vertically. This makes no sense. No, the earthquake was so strong that there was no salvation. And then why are they still standing there? The same thing applies here. We can see multi-story buildings similar to these, completely destroyed, and these are still there. They did not fail. Similar geometry, similar number of stories. This makes no sense. This is in Kahramanmaraş in Turkey. You can just barely distinguish the slabs. 1, 2, 3, 4, 5, 6, 7, 8, 9. So best case scenario, this was a 9-story building, reinforced concrete structure, right? And behind it, you can see other 9, 10-story reinforced concrete buildings. But this building was completely destroyed. This was, here we can see a luxury reinforced concrete building in Antakya, which was also promoted as not only heaven on earth, but an earthquake-resistant structure that will offer cheap solution for the housing problem that Turkey was facing. So here we can see the Trent Garden residence in Malatya, which is an 8-story reinforced concrete building. And behind it, we can see a 4-story reinforced concrete building. And after the earthquake, as you can see, this is the sign, and now this is the new position of the sign. And you can see the reinforced concrete building behind it, which is a 4-story, that is still standing. One might say, maybe the characteristics of this earthquake were harsher for 8-story building. We'll say, okay, let us actually go and check that. This is the elastic spectrum, right? 4-story building around 0.4. By the way, the old Cypriot code has this formula, had this formula, but now it's obsolete. But again, number of stories divided by 10 is roughly the fundamental period of a reinforced concrete structure. So here it says that 0.75 G is the expected elastic spectrum acceleration. And for 8-story buildings, which is the average value between the green and the red line, is around 0.6. Now, if we go to the inelastic spectrum diagram and see the exact same thing, we will get a 0.3 and 0.25, roughly, right? So this means that the 4-story reinforced concrete building will develop, is expected to develop larger spectrum acceleration, so larger inertial forces relevantly. So in that case, the 8-story building that was 3 years old, brand new, completely collapsed. And the 4-story that we've seen there, which looks like, I don't know, at least 10 years old, right? This is not very clear. Did not develop significant damages. Again, makes no sense. This is another case, the Hotel Afsar in Malatya. And this is the after picture. As you can see, it collapsed. And behind it, the building, which was similar to that, didn't suffer significant damages. Now here again, we have high, tall buildings. Again, why are they still standing? And this one became completely flat. Now, if we can see here, and we zoom in where the rescue crews is standing, and we play a bit with AIs, given that is not very trendy, we can see that these reinforced concrete pieces that are the leftovers of the slab, this is pure concrete. There is no reinforcement there whatsoever. Again, same thing, remember Adana, right? Very important, Adana. Again, somebody is looking for survivors. If we zoom in, for those that are familiar with earthquake resistant design of structures, this is not even the bare minimum. Again, if we zoom in here, which is what this was supposed to be, structural member, reinforced concrete structural member, again, no stirrups at all, and these rebars, I mean, is not even the bare minimum. This again in Adana of another multi-story structure, and if we zoom in here, you see, and we again apply an AI software to clean a bit the photo. Look at this. This is the longitudinal reinforcement of what is supposed to be 15-story building plus. A 15-story reinforced concrete building designed and constructed at a highly seismically active area has no reinforcement. This for us is no reinforcement. So now I think it's pretty clear what my point is here from the videos that we've seen and from the pictures. I also wanted to show you here a few failures in different churches and mosques. This is the Roman Catholic Church, and this is in the Hatay province. This is before and this is after. As you can see, Mother Nature doesn't distinguish between Christianity and Islam. As you can see, this is a new mosque in Maladia, before and after, complete disaster. And let's say, okay, this is a new building, we can build it again, right? Improve it. But what about historic buildings, buildings with historical significance? This is the Adiyaman Ulu Grand Mosque, and this is the Sirvani Grand Mosque. And as you can see, before, after, and again, this is a complete disaster, not only a financial one, but a historical one. This is the historic Gaziantep castle in southeastern Turkey. As we can see here, part of the wall failed, which shows that this earthquake also had high frequencies that caused this ancient construction to collapse. And I say high frequencies, why? Because this structure and masonry walls usually are thick, massive structures with, in this case, small fundamental periods. Other types of failures occur due to soil, and in this case, soil liquefaction. As we can see, this construction didn't develop significant damages, and it, though developed a very large angle due to the rotation, due to liquefaction. So this means that the soil under the foundation, which as we can see here, the foundation, it's around 1.5 meters thick. So one good way to calculate the thickness and as a starting point is to take all the thicknesses of the slabs above, add them together, and the summation is, in this case, a very good estimation. So yeah, 7 times 20 is 140. So this means that the design was adequate. But again, the geotechnical design was not performed, maybe at all, or they did not catch what happened a lot during the Izmir earthquake in 1999. Many structures failed due to liquefaction, and in this case, this is a standard case of liquefaction. By the way, this is what it looks like, part of the structure that actually completely collapsed, and the rest that tilted hit the structure behind, but it did not develop significant damages. So this means the superstructure was adequately designed, but the foundation system that was selected was not appropriate. Now, if you remember in slide 9 where I showed you Prof. Gana's, in that case, pattern, the rupture surface. In some areas, there were even 8 meters of slip that reached the surface. This is the case of the Kahramanmaraş-Gaziantep highway, which resulted into a 3 meters rupture. This is a road in Turkey which was completely destroyed after the earthquake, And this is the damaged D420 road in Demirkopru. I hope I pronounced this properly. Also, this is the Hatay airport, where we see here a corresponding geotechnical failure. And of course, this runway is completely lost. It needs to be fixed. Nobody can use it. And I am sure there are many, many other cases, but we don't have an infinite amount of time. So let's go back to that lovely claim that the earthquakes were so massive that no code could have saved the buildings. And let's see if that was a true statement. Now, this is the Turkish Construction Association building. And as you can see, it's the only one standing. And around it, we just have rubble. Mr. Yasar, I saw this interview in a Greek channel, but I'm not sure if he's the president of the Turkish Construction Association or if he's affiliated. These may be some of my students that are from Turkey, they can confirm this. He said that their building was the only one who followed the design code regulations, and most of the buildings constructed prior to theirs did not have permits. And of course, this is a picture that actually depicts exactly what that means. Now let's see what Mr. Erdogan was stating 4 years ago. This was March 2019. It's in Greek, so I will, and Turkish, so I will translate it to you. With the zoning regulation and the building amnesties, we solved the problem of 144,556 citizens in Kahramanmaraş. So the government stated, you can pay us a fine and we will legalize your illegal structures. Of course, here the Greek reporter says this haunts now Mr. Erdogan. They have elections really soon. They are down by 14 points, by the way, if you see international news. And they did it to attract people and vote for them. So it says here, these are paper buildings. With this zoning peace, so they were coming in peace with the owners that had illegal structures. With this zoning peace, regulation piece, the problems of 205,000 citizens of Hatay were solved. So this is what he stated back then. And not only that, now you'll see some more failures. They created advertisements on TV. Now I'll show you one of those right now. So these advertisements were promoting this zoning piece, these building amnesties. Oh, Mr. Hassan, the lady says, so as for us to not stay in the outside, I just translated really fast, we constructed 2 houses. We constructed them extremely fast. So now we are living with the fear that they will be destroyed. It's not the correct translation, I believe, because the municipality has to demolish this type of structure, so they live in fear that they will be demolished by the government and by the local government. Will the government and the city, let's say, come in peace with us and allow us to keep our houses? And he says the state is here to solve the problems of all citizens. Now you can connect your electricity, you can connect electricity, water, and natural gas to your house. Electric, he said it, right? I mean, it makes sense. So, unfortunately, this was the situation, and you can now understand from the numbers on how many building amnesties they offered to people, why we had this huge number of deaths and collapse. Also, they were stating that contractors were building brand new 8-story, 10-story, 15-story buildings, and they were just approving by themselves the drawings and the construction and giving themselves the permits because they could do it. The Erdogan government issued more than 130 arrest warrants, Some of the contractors were arrested at the airport trying to flee the country, so it was a complete mess altogether. Now, before we move to the case of the Ezrin city, which I find to be very interesting and very important, we should say a few things also about the damages in Syria. Like 900,000 plus people were in urgent need of shelter, and of course a lot of died. And just a point of view here from schools that were not able to be used anymore after the earthquake, 464 schools were damaged and 126 were used as a shelter. So this means that the aftermath also was devastating, and it's still devastating, and it will be devastating for these countries, and especially like a city of Aleppo. I was coming with this name from the war, right? The Syrian war. Now the earthquake came there to finish what was left, and here we can see people that are trying to take out and remove and rescue a girl from the rubble. This is the damage map in Syria, and we're going to see also the same map for Turkey. The darker the color, the higher the intensity and more damages occurred. So the case of Ezrin city. Some people spoke, by the way, about a miracle. So as we can see, this is Ezrin over here. This is the epicenter, 7.8 in the moment magnitude, and this is Kahramanmaraş. And remember, by the way, the 4-story reinforced concrete building, 1-story reinforced concrete buildings, 2, 3 stories. So up to 5 stories were the buildings in the city of Ezrin. Of course, don't remember that the fault was 250 kilometers long. So if I want to draw it here, I won't be able to do it because that's not 250 kilometers, right? So now let's see why people spoke about a miracle. This is Ezrin, where the arrow shows this is the location of the Ezrin city. Do you remember I told you to memorize some names? Adana. This is the epicenter over here. Ezrin is closer to the epicenter than Adana, actually half the distance. As the waves travel, the intensity decreases. Malatya, way further. Hatay, also further. And what happened in Ezrin city? In this city, the officials and the residents stated that there were no deaths and no building collapses. And of course, when they were asked why, they said that we did not allow any constructions, illegal constructions, to be not only constructed, but after they were found, after they allocate and they found an illegal structure, they will actually demolish it. So the NBC News interviewed Mr. Emre, who was 6 years working for the municipality, and he said that whenever the officials realized that there were buildings that had been illegally built, they would demolish them. And of course, we all understand that people were living in them, and those people were really mad about it. But the mayor held firm, and he proceeded with the demolition. And after the earthquake, the city's population increased by 50% because a lot of people went there to find refuge as well. And of course, it's logical to understand the before and after in this case, which is what we need to see. Now with this, we reach the point of the conclusions. So the first conclusion is that indeed, these earthquakes were large. And our design codes do not take into account the intensity that these earthquakes eventually produced, especially 2 main events within 9 hours between them. Nevertheless, though, as we've demonstrated, and as we've seen from a lot of pictures and videos, the knowledge that we have today to design reinforced concrete resistant structures can and would have allowed us to prevent any failure even for this type of earthquakes. The reason why this did not happen and we had a complete disaster is mainly attributed to the building amnesties that the government was giving, contractors that they did not comply with the country's code, and of course, poor quality construction material. Concrete that behave literally like sugar, like sand. And of course, in other cases, we had an inadequate know-how and lack of fundamental earthquake resistant design knowledge from the civil engineers that designed their structures. Could have this been avoided? The answer is yes, simply by implementing the design codes of the country properly. And of course, nobody says nothing would have collapsed, but definitely this level of disaster would have been avoided, at least by 90%. Was the city of Ezrin really a miracle? I'm sorry to say to those that believe and they are really religious, it was nothing but a miracle. What was a miracle, at least to my understanding, was that we had a non-corrupted politician, the mayor. That was a miracle. And this is what saved them. And that's why the Ezrin city now knows who's going to be the next mayor. Does this mean, though, that our design codes work? We should not improve them. We should not change them. No, Turkey should change their design codes, and Eurocode is a very good starting point. And now this current flexibility that is found in the Turkish code should be completely removed. And last but not least, unfortunately, we do learn, and especially in civil engineering, we do learn from this type of disasters, which as academics and civil engineers, we would like to avoid by any means, but they do happen, as we can see, because we cannot control the built environment. And therefore, according to what I've seen thus far, the toughest lesson learned today is that corruption kills. Now, this is not only a common English proverb, it's also the title of the publication on Nature Journal by Nicholas and Roger in 2011. On the anniversary of the Haitis earthquake, the devastating earthquake that killed hundreds of thousands of people, they discovered that 83% of all deaths from building collapse in earthquakes occurred in countries that are anomalously corrupt. So it's not only a theory, it's also mathematically proven. And I chose to close with this picture here because as a father myself, every time I saw this picture, like it was devastating and sad. Like we see here a father sitting on top of a crime that has just been revealed, holding his dead daughter's hand, waiting for somebody to come and remove her dead body from the rubble. So as you can see, practically there is no reinforcement in this reinforced concrete structural member. Thank you very much. So if anyone would like to ask something from the people that are online. All right, Özlem says that I pronounce the names really well. Thank you. I will switch back to my camera. I will stop sharing the screen. Thank you very much for your attention. If you have any questions, if you want to ask about the earthquake or modeling, thank you, Johan. The floor is yours. Yes, Prof. Hannes.
Prof. George, just a question about materials and so on. I'm just curious, what is the availability of good quality aggregate, sand, cement, steel in that part of the world? And
price wise, etc.
Now, coming from an earthquake active country myself in Cyprus, we solved that problem a long time ago by having specialized companies that they produce concrete and they are responsible in order to provide with high quality material, right? If I have 20 megapascal uniaxial compressive strength, they will send me most of the times 25 or even 30. So that's quality control. Plus the corresponding specimens that we get, usually cubes, in order to check that this material is correct. Now, if we fly over northern, right, to Turkey, we are now dealing with a society which is normal for somebody to say, I need a house, and they will start constructing it without the help of a civil engineer. God knows what type of materials they use. And of course, concrete is not high quality concrete. And then you see structures collapsing in a completely vertical manner. Then you have the structures that, let's say, they have quality concrete, but they don't have steel. The reinforcement is nowhere to be seen. This is evident. I mean, everywhere, any structure that you see, any rubbles that you see, you're looking to find the reinforcement and you can't find anything. So yes, again, with all the respect to all my professors that I'm really lucky, I was really lucky to have them as my professors, and they are really well known. The first thing that everybody started saying, oh my God, in front of the entire country, these earthquakes were massive, and this is the reason why everything collapsed. But that is not the case. This is not true. So this is what I found through my own research. And some of those professors went there, and then they started changing the tune. They started looking at the rubble. They said, oh, we couldn't find reinforcement. Material was, even a MAC, the special forces in Greece that went there to help. They were interviewing them, and they were stating 60% of the structure, we haven't seen this never in our lives. Like concrete wasn't concrete, it was like sand. So this was evident that corruption kills. Yes.
Thank you, Prof, for the presentation. My question would be, if such low quantity materials was used
Illegally.
or illegally being used, would we have seen failures of the structures because of the materials not being able to resist tensile forces due to normal collapses over time, maybe, instead of an earthquake? And have it been observed?
We see that in Cyprus as well and in Greece. Every now and then you see the balcony cantilever, right? Collapse and almost kill somebody that was working there. And then you go there and see, especially in Cyprus, we are an island, right? So chloride and elements that are corrosive to reinforced concrete structures are everywhere in the entire island. So if you don't design your material property, if you don't use proper concrete cover, and in my country, especially after the invasion in 1974, the war, right? That a lot of houses were needed to be constructed, and they started building really fast, and they were using aggregates that they were not up to standards, and they had elements that they were corrosive to the concrete itself. Then you see cracking, spalling, reinforcement that is rust, and then eventually, due to the self-weight, some of the verandas and the balconies were collapsing just like that. Now, one very interesting question, and everybody is stressed there, right? The journalists, they ask you, are we going to experience something similar in Cyprus and in Greece if this type of earthquakes will occur? There is not a chance in the world that we will see what we've seen in Turkey, because I've been there. I know my colleagues in Greece and civil engineers, and they will never allow something like this to happen, and I've never seen anything like that in any construction in Cyprus and Greece. Like, we know we will have earthquakes. So even if I'm going to make money, Worst case scenario, say the designer used 20 millimeter in diameter reinforcement in the foundation. I will use 16 or 14 because I know my experience tells me that he over-designed it. So I will optimize my design, but not leave it without any reinforcement at all. I mean, you know that these earthquakes will come, and earthquakes, they are not like government or politicians. If you know them, they will make an exception and give you the position. They will reveal everything. This is the first thing that we've learned when we study earthquake-resistant design. Earthquakes reveal, the earthquake is God. It will reveal any mistakes in your design, and especially in the construction. So it's all about proper implementation at the end of the day. Yes.
So the question is, the fully designed buildings in that region, or is it only in that portion of Turkey, or is it
Everywhere. It's everywhere. The government had ads saying, everyone, come and pay. Legal structures, legal, and allowing them to connect electricity, water, and natural gas. So, and they knew that area well, and the contractors knew. Imagine what they have in their brain. Like if I make even 10 million and then kill 50,000 people, how will I be able to sleep during the night? Personally, I wouldn't. Some people can. I wouldn't be able to do it. Maybe one of the reasons why I became professor, to teach people like you and be able to preach. I did work in the industry a lot, and we even investigated nuclear reactor buildings under mega earthquakes, but you have to be meticulous, and whatever you do, if I tell them, look, this structure, even a nine moment magnitude will not touch it. I need to be 1000% sure that this is the case. In that case there, they were just doing whatever they wanted to save money from reinforcement and exploit the poor people of Turkey, which my prayers go to, and the people of Syria, of course, as well. So can we take some, do you have a,
I see there's a couple.
please, so Prof. Hannes will be able to read our questions online, and I will try to do my best to answer them.
Okay, the first one says, can you please comment briefly on damping technology?
Yeah, and I see Shane Hossel as well refers something about New Zealand. The case of New Zealand recognized as well that our current design of earthquake-resistant structures for season allows us the damage development. And in New Zealand, after the earthquake, we had 70% of the structures had to be demolished, even though they did exactly what we asked them to do. Save everybody that's inside and outside. So we didn't have failures, but they developed damages at such a level that we had to demolish them, and that didn't sit really well with the owners. And then people started asking about, all right, are there any technologies that can prevent us from developing even damages? And this is what we have here, not only damping, but seismic isolation. We have elastomeric bearings, we have friction, and of course other techniques, including damping, that will absorb, let's say, consume the energy of the earthquake during the oscillation of the structure and avoid the generation of large damages. Shane, I hope I covered your question. Is this what you wanted to ask? Again, and Shane also says about proper detail. Again, if I detail my structure properly, right, and I design it for a 0.25 GP ground acceleration, and I get a 0.6, and also I design it by taking into consideration that my structure will behave in a non-linear manner through the behavior factor. If I use the behavior factor, a lot of civil engineers don't understand what this behavior factor is. The behavior factor allows us to decrease the expected seismic load by assuming that our structure will behave in a non-linear manner because it will develop damages, plastic hinges, and it will still have the ability to resist to load. So this means that by default, we allow our structures and our designs to accept damage development during an earthquake excitation. And we do that in order to keep the cost at bay, right? To maintain a balance between cost and, in this case, safety. And it works, but like in the case of New Zealand, it did work, but it didn't work very well for those owners that had to demolish their entire buildings, which were like 10 stories or more, and building new ones. So that was something that they took into serious consideration. One might say, all right, how much does it cost to seismically isolate the building? So approximately 15% of the cost of the framing system is the increase in terms of cost. And if you're willing to pay for that, you will never have to worry about earthquakes again. Plus, in 2003, with Professor Gazetas, we went an educational trip to Japan. We visited the defense facilities, the seismic table, and in that case, we visited the research facilities of the 5th largest construction company in Japan. It was a huge box that was founded on 6 circular piers, right? Huge columns, and seismic isolation, elastomeric bearing, standard reinforced elastomeric bearings were used. And I had a colleague there that she was a student that was doing her master's back then in Japan, and during a 5-point-something moment magnitude earthquake, she found herself in those facilities, and they went out and they saw people in the street, and they said, what happened? There was an earthquake. They said, oh, they didn't feel a thing. So even the elevator was hanging from the framing system of the structure. And we know that most of our bridges use this technology to decouple the deck from the piers, in order to avoid stress concentrations when we have trucks and cars using the deck, right? In order to avoid fatigue failure and cracks due to fatigue failure. And therefore, bridges are the last structural members usually that develop any damages, unless the earthquake is so large and the fundamental period is close to the fundamental period of the bridge, and we have things that the designers weren't expecting, like the Auckland Bridge in the States and so on, and we have failure. And the bridges in Japan that failed in 1995 were a lot, and that was because the old Japanese code was not sufficient and enough for the earthquakes that actually Japan expects to have and experience. That's why they updated it. And that's why that 1995 was an earthquake with a 0.35 G. The Turkish one was 0.62, right? At least the one that I found for the EMS, and it cost them $200 billion in damages. The Turkish earthquake, 34 billion. It was a smaller earthquake, which caused significantly more damage, right? But of course, again, each and every earthquake is like a fingerprint. They are different intensity, different frequencies. Then you have the soil structure interaction, a recent research project that we had on the nonlinear dynamic response of reinforced concrete structure, including the soil structure interaction phenomenon, taking into consideration material nonlinearities in the soil and 3D detail modeling with material nonlinearities in the superstructure. And by calculating the fundamental period of the frame when after it started developing damages, we found out that there is a chance of the damaged framing system will develop a new fundamental period because it evolves, and you take into account the stiffness as well, which changes. And then you can actually have a resonance with the fundamental period of the soil itself. And then a structure that was expected to develop smaller deformations is the one that will be led to complete failure. Instead of, let's say, a fixed structure, a structure that is found on soft soil. So the problem is way more complicated than the design codes assume it to be. Yes, Prof. Hannes.
There's a few more questions, perhaps a quick one. It's asking, do you know what the relationship is between the failure of new buildings compared to the older ones in this earthquake?
This is a very, very nice question, and I was also planning to add it, but I had already 76 slides. There should be a statistical analysis on each and every type of building that failed, including age, number of story, and if possible, maybe the size of the plan view. So we actually can use that and further reinforce all the findings that I presented here today. But the answer is no, right? Because I didn't even have the chance to go there. The country now is struggling and they have elections. So you can imagine now everybody's pushing money in promoting their candidate. And yeah, this is really a sad story, and the one that always pays the price is common people like you and me, and the people, you and me, I mean people that you are connected now and watching this presentation.
Thank you, yes. Saurabh asks, can you quickly revise? I'm just putting my sound on so that they can hear you.
I'm muted, yes?
Can you revise that spectral acceleration slide with the 4-story and the 8-story
Of course.
comparison?
That's the essence, by the way of understanding how things work. So, can you see it, by the way? I mean online. Can they see it online? I shared my... It's there, right? Okay. So as I said before, civil engineers found a way, a simplified way, to design their structures under seismic loads. Instead of performing a dynamic analysis, we said, instead of running through time and trying to find what's the maximum expected load, let's reverse engineer the problem and find a quasi-static load which will represent the maximum expected seismic load that any structure will develop due to this earthquake. So in this case, if we use the inelastic spectrum diagram that was developed by using our seismospect, the x-axis represents the fundamental period of any structure, and the vertical axis represents the inelastic spectrum acceleration that any structure will develop. If we know the fundamental period, which we can calculate either by using a finite element analysis software or a design code, T 0.75 height of the structure to the power of 0.75. This is the Eurocode 8 formula. Or you can use an artificial intelligence generated predictive model, which we published recently, which is not only 100 times better than the design code, it also allows you to take the soil structure interaction into consideration. So let's say I have not any of those, and I say, Cyprus code, number of stories divided by 10. I have a 10-story building, 10 stories divided by 10, 1. 1 second, we are here. Go up, we are there, go left, around 0.20 something G. So this is the maximum inelastic spectrum acceleration that I expect my 10-story to develop. And if I know the mass that is going to oscillate during this earthquake excitation, I multiply spectrum acceleration by the mass, and then I get the seismic load. I distribute it along the height, and then I have my load, my seismic load, which I will combine with my dead and live loads, and this is my seismic load combination in order for me to perform the analysis, get the maximum expected bending moment, shear, and axial forces, and then design each and every structural member and make sure that they will be able to resist to those loads. So in this case, this is the simplified way, which works, that us civil engineers use according, in this case, to Eurocode. Of course, one might say, yeah, but this is a spectrum acceleration from the earthquake. What about the code? In the case of the code, we will use this blue line. This blue line changes according to the type of soil, according to the location that our structure is located, like in Greece, Cyprus, and here in South Africa, when I teach my students, we have the map with the maximum expected ground accelerations. Within the code, you go say, I design in Pretoria, or I design in Limassol, or I design in Athens. I go to the map, I see, that area is expected to develop 0.2, 0.25, 0.3 G, peak ground acceleration. And eventually, this blue diagram derives, which is Eurocode, and then I say, what is my structure? It's a 6-story, 0.6 approximately, right? This is what I expect to get, 0.6 G. This is the elastic, by the way, and we will never use a 0.6 G because it's massive according to Eurocode. According to reality, though, and according to what happened in Turkey, definitely, if we were the unlucky ones and our buildings were actually found near the epicenter and in a radius of 50 kilometers from the epicenter, then there we would have expected at least 0.5 G peak ground acceleration. I don't know if I covered.
I think you did it well.
Okay.
There's a question from Yuri Andorf. How would one retrofit historical buildings for earthquakes?
Give me a second because I can't hear you talk.
FRP
I don't know why you get muted. All right, I muted you again. Please repeat the question.
It's just that if I say the question and nobody hears it, but I'll try and speak up.
Yeah.
So how would one retrofit historical buildings for earthquakes? FRP wrapping is a popular option, but might not be suited for historical buildings regarding heatings, for example.
So, yeah, the question is about retrofitting historical buildings. The biggest problem with historical buildings is that we cannot touch them, at least from the outside, and change the way they look. So the most efficient way is to intervene at the level of, if we can, at the level of the foundation, right? So like in Japan, when we visited Japan, we saw entire buildings that they were already existing buildings. They constructed at each and every column special foundations, they lift them up, and then they placed isolation, seismic isolation pads in that case, rubber pads. So, and this is another interesting point that we've discovered recently, a publication in 2021 that investigates the retrofitting techniques. And I found, in that case, I was the sole author. I wanted to publish one publication by myself, and that was the one, never again, always with teams. I discovered that if civil engineers decide to go to a framing system and increase the strength of the columns by using carbon fiber reinforced polymer sheet, then if they applied only at the columns, they are actually endangering, worsening the ability of the structure to resist an earthquake. Why? Because they strengthen significantly specific parts of the structure. They mitigate the damage development within structural members that they are not ready to develop additional strains and stresses. And then when the structure is called to resist and provides us with everything it has, it fails faster than the actual initial framing system. So it's not as straightforward and simple as people think. And I see so many pictures on Facebook, and they show there is a Piskevés and something on Facebook, which is a Greek page that everybody is posting their works of retrofitting and strengthening of existing buildings. And you see columns which are strengthened, which is done in a proper manner, and they just increase the thickness of the columns, and they have no idea how that will affect their overall mechanical and dynamic response of their structures. And the only way to do it is by using, in this case, technologies which allows us to investigate the exact expected mechanical response of our structures, which is, in this case, 3D detailed modeling through finite element analysis. And in the future, I promise you, I joke you not, through AI. This is the best tool that we have right now, currently, in evaluating the interventions that we actually perform on our structures. The other way is to go construct it and perform an experiment in the laboratory. I don't think a 1 million euros or US dollars experiment will be something that we can easily perform. And it has its limitations. Like that, a 6-story reinforced concrete building was one of the largest specimens that were ever developed and tested under dynamic loading, because you need a bigger seismic table in order to accommodate a bigger structure. Cost-effective wise is useless. I mean, there is no merit there eventually, because the cost will be so high.
Quick, people are asking about the slides, and you said you will make it available on.
Upload these as it is, the presentation on LinkedIn. Anyone that is not connected with me on LinkedIn, send me an email, and I will gladly send you back the PDF file, no charge. Free of charge, right? So my email is found also on LinkedIn, but just for you to have it here, this is george.markou@up.ac.za. University of Pretoria, one of the best civil engineering departments in the world.
There's a hand from Dima. Perhaps
Dima, she was my former student. Yes, Dima. In
Yes,
the UAE.
just,
Where are you?
how are you? How are you, doctor?
Okay, Dima, how are you?
I'm good. Just want to say this is a pleasure to attend again one of your intelligent lectures. Thank you very much for the all information that you shared with us. And I'm always glad to attend all of your lecture. So thank you very much for this opportunity, doctor. Thank you again.
You are most welcome. Thank you. You make me blush now. Okay. Any
This is the
questions
truth.
other than nice words?
there's a question. Is it better then to have more redundancy in your structure, or to design your structure with higher strength concrete when you want to build earthquake-resistant structures?
Now, this is a very interesting question, and anyone that has been evolved with earthquake-resistant design structures, plus has gotten deep into soil structure interaction, knows that and understands that that question shouldn't be a question, because you need to be dynamic and choose the appropriate framing system and material according to the geometry of your structure and what the foundation system is going to be, plus the mechanical properties of soil that your structure is going to be founded on. So it's a multi-parameter problem that if you construct a high-strength concrete structure with the same geometry and another one with a lower strength concrete, and therefore the structure with the high strength is more rigid, and an earthquake strikes which is high frequency and it resonates with the one which is more rigid, even though it's high strength, it will develop more damages and it might collapse, and the other structure will feel nothing, or it will develop significantly less damages. So there isn't a secret recipe. There are rules that you have to implement and then eventually end up with a structure, which is of course what Eurocode requires from us. As civil engineers, you will end up having a final product that will mitigate most of the risks as much as possible when an earthquake occurs. I hope that makes sense.
We have 5 minutes left, so I'm going to just, we don't have time for everything, but this one is related to this question. It says, do you think code-based design is a way out of this kind of earthquake over-performance-based, full non-linear-based design approach?
A straightforward answer, and because I understand what the question is all about, and the one who posed the question wants me to say, no, it's not, which is mostly true. On the other hand, not everybody can afford seismic isolation, or structures which can decouple, and joints that will be so flexible that will not allow for any damages. So the truth is always in the middle. And we're talking now about a country that they cannot even afford to construct not a seismically isolated structure, but a structure that will at least cover the bare minimum in terms of reinforcement and quality of materials that not Eurocode, but their code requires, which is not as strict as Eurocode, because we know Eurocode is a code that does not allow any leniency or flexibility, or don't design for that because you're this, or it's either black or white. It's like plus or minus. So yeah, this is my answer to this highly complicated question. And I say it's highly complicated because if we take into consideration finances, and if we come to a part of the world like South Africa, where people, and a big portion of the people, struggle to find food and money to buy food for their families, you cannot talk about seismic isolation. There are way, way more serious problems than seismically isolating buildings here in South Africa. And the same thing applies partially in Turkey, even though in Turkey it will make sense to apply a code that, if at least a structure is higher than 10 stories, you should be obligated, let's say, to seismically isolate it in order to protect the people that are in that hotel or in that residence or in this huge building that is full of offices.
Right, Prof. Markou, thank you very much for surely a very interesting presentation.
Let me stop the recording here. Thank